For 70 years, computer chip has meant one material: silicon. Every phone, every laptop, every AI data center on Earth runs on transistors carved into wafers of the same element, refined from ordinary sand into some of the purest, most precisely engineered material humans have ever manufactured. That single material choice has underwritten the entire digital age, from the first pocket calculators in the 1970s to the trillion-parameter AI models running today. And in July 2026, a small startup in Shanghai switched on a production line that does not use a single gram of it. The company is called WUJI, and what it just built is the world's first full-scale pilot production line for two-dimensional semiconductors, chips built from a completely different class of material, only a few atoms thick, that behaves nothing like silicon, and according to the lab research it is based on, actually outperforms it. This did not happen in isolation. It follows a Peking University research team's own transistor, built from an element you would not expect to find anywhere near a chip factory, that Chinese researchers claim runs 40% faster than Intel and TSMC's best silicon chips, while using 10% less power. Put those two stories together, the lab result and the factory that just switched on to build it at scale, and you get a genuine question the entire chip industry is now sitting with. Is silicon's 70-year monopoly on computing actually starting to crack? Or is this another headline that quietly fades in a few years, the way so many silicon killer stories have before it? By the end of this video, you will understand exactly what these new chips are made of, why silicon is running into a wall it cannot climb over, and how close China actually is to building a real alternative rather than just a headline. If you like videos about the technology quietly reshaping how the world works, hit like and subscribe so you do not miss what is coming. Let's start with the wall silicon actually hit. Every chip works the same basic way. Millions, and in modern processors, billions of tiny switches called transistors, etched onto a wafer, flip on and off, to represent the ones and zeros all computing ultimately reduces to. For 60 years, the entire industry's strategy for making chips faster was brutally simple. Shrink the transistors, pack more of them into the same space, and let a rule called Moore's Law do the rest, doubling the transistor count roughly every 2 years. That strategy worked spectacularly well for decades, taking chips from a few thousand transistors in the 1970s to tens of billions on a single modern processor, but it is now running directly into the physical limits of silicon itself. As transistors shrink down toward 3 nanometers, a scale measured in a handful of atoms, roughly a dozen silicon atoms lined up end to end, silicon starts to misbehave. Electrons stop reliably staying where the circuit design says they should, and instead begin leaking, tunneling straight through barriers that used to contain them. A genuine quantum mechanical effect, not an engineering mistake, and one that gets worse the smaller you go. Push a silicon transistor thin enough, and it essentially stops behaving like a switch you can fully turn off, which wastes power and generates heat even when the chip is supposedly idle. Making transistors this small also requires extreme ultraviolet lithography machines, EUV for short, a technology so difficult to build that exactly one company on Earth, the Dutch firm ASML, can manufacture them. Each EUV machine costs well over $150 million, takes years to build, and depends on a supply chain so specialized that no other country, including China, has managed to replicate it despite years of trying. Largely because of ongoing export restrictions dating back to 2019, Chinese chipmakers have been effectively locked out of buying the newest generation of that equipment entirely, meaning even if a Chinese fab wanted to keep shrinking silicon the conventional way, it currently cannot legally buy the one machine required to do it at the cutting edge. Silicon is not just approaching a physics problem shared by every chipmaker on the planet. For China specifically, it is also sitting directly behind a very deliberate political wall. That combination, a material running out of physical road, and a country cut off from the machines needed to keep pushing it forward anyway, is exactly the setup that pushed a team of Chinese researchers to stop trying to out-engineer silicon and start looking for something else entirely. At Peking University, a chemistry professor named Peng Hailin led a team that turned to a completely different category of material: two-dimensional semiconductors, crystals that can be grown or exfoliated down to a single layer of atoms and, critically, keep working properly even at that thickness, which silicon simply cannot do. Silicon transistors lose their electrical properties and start leaking current badly once you thin them down anywhere close to a single atomic layer. Certain 2D materials do not have that problem, which makes them, at least on paper, a far better fit for a future where transistors keep needing to shrink. The specific material Peng's team landed on is called bismuth oxyselenide, written in chemical shorthand as Bi2O2 seth. Used as the transistor's channel, the pathway electrons actually travel through, paired with a related compound called bismuth selenide oxide, Bi2SeO5, as the gate material sitting above it. Bismuth itself is a heavy, silvery metal, more commonly associated with the pink crystal geodes sold in gift shops or the active ingredient in stomach medicine than with computer chips, which makes it an almost deliberately strange choice for cutting-edge electronics. Researchers had actually been eyeing bismuth oxyselenide as a promising material for sub-1 nanometer chip technology for years before this specific breakthrough, precisely because of its natural ability to form stable, high-quality two-dimensional crystals, something most candidate materials in this category struggle to do cleanly. But in this particular crystal structure, bismuth oxyselenide turns out to have real electronic advantages beyond just its 2D stability. Electrons move through it noticeably faster than they do through silicon at comparable scales, a property called carrier mobility, and the material also has what is known as a high dielectric constant, meaning it holds and controls an electric field more efficiently, which translates directly into faster switching and less wasted energy. Peng described the effect in terms of resistance to flow, comparing electrons moving through the new material to water gliding through a smooth, clean pipe, rather than being forced through something rough and narrow, and pointed specifically to the unusually clean interface his team achieved between the channel and gate materials, with far fewer atomic scale defects than typically show up when combining a 2D semiconductor with a conventional oxide gate, as the detail that finally let the design work as well in practice as it did on paper. The transistor design itself is also a meaningful departure from what most chips use today, though not entirely unprecedented. It uses what is called a gate-all-around structure, GAFET for short, where the gate, the part of the transistor that switches current on and off, wraps completely around the channel on all sides rather than covering it from only 3 sides the way the previous generation of FinFET transistors do. Picture the difference between squeezing a garden hose from 3 sides versus wrapping your hand fully around it. Full wraparound control lets you shut off the flow far more cleanly, with much less water still dribbling through when it should be fully closed. Wrapping the gate all the way around a transistor's channel gives it exactly that kind of far more precise control over the flow of electrons, which cuts down on leakage and improves switching speed. Gate-all-around transistors are not unique to China. Samsung has already used them commercially in its own 3nm chips, and TSMC and Intel are both moving towards similar architectures for their next generation of silicon nodes, so this part of the design is very much where the whole global chip industry is already headed. What is genuinely new about Peking University's version is combining that gate-all-around structure with a channel made from a 2D material instead of silicon, something previous attempts had struggled to pull off cleanly because 2D materials tend to have rougher, more defect-prone interfaces with the surrounding gate structure, interfaces where stray atomic scale imperfections can scatter electrons and quietly wreck the very speed and efficiency advantages the 2D material was supposed to provide in the first place. Peng's team says they solved that interface problem well enough to actually build and test working devices, and the headline result, a transistor running 40% faster than Intel and TSMC's most advanced 3nm silicon chips while consuming 10% less power, comes directly from those tests, published in the peer-reviewed journal Nature Materials in 2025, meaning the underlying data has already been through independent scientific review rather than resting purely on a company press release. A single transistor working better in a lab is one kind of milestone. A company willing to build an actual factory around that idea is a completely different one, and that is exactly what changed in July 2026. Shanghai-based startup WUJI switched on what it calls the world's first 8-inch pilot production line dedicated entirely to 2D semiconductors, unveiled on July 11th, and inaugurated with tape-out services active from around July 10th. A facility covering the full manufacturing chain, from growing and preparing the raw 2D material itself, through building individual transistors, all the way to full chip integration and something called tape-out, the final step where a finished chip design is actually sent off to be manufactured. That last detail matters more than it sounds. A huge number of promising lab materials never make it past this exact point, because growing a perfect crystal on a tiny sample in a university lab is a completely different engineering problem than reliably growing the same material, defect-free, across an entire 8-inch industrial wafer, over and over, at commercial yield. Having real tape-out capability on a 2D semiconductor line means WUJI has cleared a step where most 2D chip research worldwide, including projects at some of the biggest names in the industry, has historically stalled out. WUJI is also releasing the practical tools an outside chip designer would actually need to use the technology, publishing an initial version of its process design kit, effectively a rulebook and toolset engineers use to design a chip compatible with a given manufacturing line for its 500-nanometer 8-inch process. The company also says it intends to use heterogeneous packaging, physically combining 2D chips with conventional 3D silicon chips inside the same finished package. A pragmatic approach that does not require replacing every silicon component in a device on day one, just the specific pieces where a 2D material's advantages actually matter most. WUJI is not promising to leapfrog straight to the cutting edge overnight, and it is worth being precise about what it is actually promising. The company's chairman has said the near-term goal is a manufacturing process roughly comparable to a 90-nanometer silicon node by the end of 2026, a process silicon fabs mastered commercially more than 2 decades ago, before working toward a fully domestic process equivalent to 5-nanometer chips by 2029, explicitly without using EUV lithography at any point along the way. In other words, this is not a company claiming to already beat TSMC's newest chips at industrial scale. It is a company betting that an entirely different manufacturing path, one that sidesteps the EUV bottleneck altogether rather than trying to build a homegrown EUV machine to match ASML's, can eventually reach a similar destination. WUJI is also not working alone, and the cluster of activity building up around it is arguably a bigger signal than any single company's roadmap. A Nanjing-based startup called JMoly, spun out of Nanjing University Research and founded in 2024, has already announced mass production of its own 8-inch 2D semiconductor single crystals using a proprietary oxy-MoCVD deposition process it developed in-house, a specialized chemical vapor deposition technique for growing thin crystalline films, and is already shipping material to research groups at universities, including Cambridge and Fudan, meaning its output is good enough that serious academic labs outside China are choosing to buy it rather than grow their own. Separately, a company called Shanghai Atomic Technology activated its own pilot production line back in January 2026, aimed specifically at sub-1 nanometer processes, well beyond anything silicon could ever physically reach, with a stated target of small batch production by the end of 2026 and large-scale manufacturing by 2030. None of these companies are giants. All three are relatively young startups, several spun directly out of university labs within the last 2 to 3 years, operating on a fraction of the capital and headcount of an established chip giant like TSMC or Samsung. But the fact that 3 separate, independently funded companies are simultaneously racing to industrialize the same category of material, in the same country, within months of each other, each pursuing a slightly different piece of the same underlying problem, one focused on raw crystal supply, one on a full pilot fab, one on pushing toward the most extreme process nodes, suggests this is not one lab's isolated result being amplified by state media. It looks like the early shape of an entire new supply chain forming at once, the same pattern that historically shows up right before a genuinely new material category actually breaks into commercial use rather than staying a permanent research curiosity. There is a reason this particular breakthrough is landing at exactly this moment, and not, say, a decade ago, when 2D semiconductor research first started producing promising lab results. The global AI boom has turned raw chip performance into a genuine strategic resource, not just a consumer electronics talking point, with the most advanced AI models on Earth bottlenecked as much by how many cutting-edge chips a country can access as by any algorithm. China's access to the newest American AI accelerators has already been sharply restricted for years, and its access to the equipment needed to manufacture equivalent chips domestically at the leading edge has been restricted right alongside it. A material that could theoretically deliver a meaningful performance jump over silicon, arriving at the exact moment the country training its own AI models most needs every available advantage, is not a coincidence of timing so much as the entire point. None of this is happening in a vacuum more broadly either. China has been pouring state investment into semiconductor self-sufficiency for years through vehicles like its National Integrated Circuit Industry Investment Fund, commonly called the Big Fund, which has directed tens of billions of dollars into domestic chip design, equipment, and materials companies since 2014. That effort has recently produced other headline-grabbing workarounds to the same underlying EUV bottleneck. Huawei announced its own approach in 2026, a chip design technique it calls logic folding, which achieves higher effective transistor density not by shrinking transistors further, but by folding and stacking conventional 2D circuit layers into a vertical 3D structure instead, aiming for the equivalent of a 1.4 nanometer process by 2031 without needing EUV lithography at all. Separately, reports emerged in July 2026 that a Chinese firm had begun manufacturing its own immersion-deep ultraviolet lithography machines, a less advanced but still genuinely useful tool already reportedly under evaluation at China's largest chipmaker, SMIC, targeting older 28 nanometer processes today, with a roadmap towards 7 nanometer and even 5 nanometer chips through more complex multipass exposure techniques. Two-dimensional semiconductors are not China's only bet against the EUV wall. They are one of at least 3 parallel bets: chip stacking, homegrown DUV lithography, and now 2D materials, all aimed at the same underlying constraint from completely different angles at the same time. It would be dishonest to end this story sounding like silicon has already been dethroned, because it very much has not, and the gap between what has actually shipped and the headline claims is worth sitting with honestly. Yuanjiwei's pilot line is explicitly described, even by the company itself, as an engineering validation facility, built to refine manufacturing processes at small scale before any future expansion to real commercial volume, not a factory currently shipping chips into phones or laptops. Its near-term target, a 90 nanometer equivalent process by the end of 2026, is roughly 15 years behind where TSMC and Samsung's leading-edge silicon fabs already are today, and the more ambitious 5 nanometer equivalent target sits 3 full years out, in 2029, contingent on manufacturing problems that, as of today, are still unsolved. Peking University's headline transistor, the one that started this entire story, is also still fundamentally a single, individually tested device built and measured in a university lab, not a working processor with the billions of interconnected transistors a real modern chip actually needs, each one manufactured identically and reliably across an entire wafer. Going from one working transistor to a billion working transistors, wired together without a single fatal defect anywhere in the chain, is historically where breakthrough chip materials go to die, and it is a problem silicon itself took decades of dedicated global investment to fully solve. Growing a defect-free 2D crystal across an entire 8-inch wafer is dramatically harder than growing one on a small lab sample, because every additional square centimeter is another opportunity for the atomic scale flaws that ruin a transistor's performance, and the industry does not yet have anywhere close to the decades of accumulated process knowledge for 2D materials that it has for silicon. A single stray defect in the wrong spot on a modern chip, one with billions of transistors packed onto it, can render the entire chip useless, which is why silicon foundries spend enormous sums on defect control and why yield, the percentage of chips on a wafer that actually work, is treated as one of the most closely guarded numbers in the entire industry. Nobody outside Yuanjiwei, JMOLI, or Shanghai Atomic Technology currently knows what their real yield numbers look like at 8-inch scale, and none of the public announcements so far have included one, which is itself a meaningful gap in an industry where yield is usually the very first number a serious buyer asks for. Cost is an open question too. Silicon benefits from 70 years of relentless cost reduction and a global supply chain built at almost unimaginable scale, from sand mines to wafer fabs to packaging plants spread across dozens of countries, refined through trillions of dollars of cumulative investment. A brand new material starting from a handful of pilot lines has none of that yet, and there is no guarantee the economics ever converge on something cheap enough to actually displace silicon in ordinary consumer products, rather than staying confined to a narrow set of specialized, high-value applications where the performance gain alone justifies a much higher price tag, at least for the first several years of commercial availability. Western researchers at institutions including MIT, IBM, and the European Research Center IMEC have also been studying 2D semiconductor materials like molybdenum disulfide for well over a decade, without any of them building an equivalent industrial pilot line yet, which tells you the scientific starting line here is genuinely global, not a purely Chinese discovery. What is different in China's case is not the underlying science. It is the apparent willingness to fund and physically build real industrial pilot lines years before every open manufacturing question has actually been answered, betting that the fastest way to solve those remaining problems is inside a real factory, not another decade inside a university cleanroom. Zoom out, and this fits a pattern that keeps repeating across China's technology strategy right now, whether the subject is chips, batteries, or energy. Faced with a hard external constraint, in this case, export controls specifically designed to cut the country off from the equipment needed to keep advancing silicon, the response has not been to simply try harder at the same approach everyone else is using. It has been to fund an entirely different technical path around the constraint altogether, at multiple competing companies simultaneously, and push it from a university lab into a real physical pilot factory as fast as possible, well before the science is fully settled. That strategy does not guarantee 2D semiconductors actually replace silicon at scale. Plenty of promising chip materials over the decades, gallium arsenide, carbon nanotubes, graphene transistors among them, have looked briefly like the future and then quietly stalled out on cost, yield, or a manufacturing problem nobody could crack in time, and 2D semiconductors could easily join that list rather than the list of materials that actually made it. But the underlying wall silicon has run into the leakage, the shrinking returns from further miniaturization, the EUV bottleneck, is real and getting harder to ignore for every chipmaker on the planet, not just Chinese ones. Every major fab in the world, regardless of which country it sits in, is quietly funding its own version of what comes after silicon research right now, because the physics does not care whose export control list you are on. Someone was always going to seriously try building around it commercially, not just publish papers about it. Right now, China is the country with 3 separate startups and a major university physically doing it, years ahead of anyone else turning the same lab-scale research into an actual pilot factory. Whether that head start turns into a real industry or another abandoned prototype sitting next to gallium arsenide in the history books is genuinely still an open question. But for the first time in 70 years, it is at least a question worth asking seriously. If this video showed you a piece of the chip world you had not seen coming, hit like, subscribe, and turn on notifications so you catch the next one. And here's a question for the comments. If silicon really is hitting a wall it cannot shrink past much further, do you think the chip that eventually replaces it comes out of a lab in Shanghai or Beijing, or does the rest of the world's semiconductor industry get there first?